A graph database is designed to store and manage data in the form of graphs rather than tables, as in relational databases. In a graph, data is represented as nodes, edges, and properties. Nodes represent entities or objects such as people, places, or products. Edges represent the relationship between nodes such as friend, owns, or friend of. Properties are attributes or details that describe nodes and edges, such as person's age or the date of purchase. Another example shown on the screen represents a graph that describes a scenario within an academic environment. The graph highlights two different parts that illustrate the semantics and instance of a specific moment. More details on this will be discussed later in this video. How graph databases differ from relational databases. Graph databases are highly effective in applications where relationships are crucial. In a relational database, modeling a network with many-to-many relationships across various entities involves numerous joins table, which can be complex and slow with large datasets. In contrast, graph databases store relationships directly in the graph structure, allowing for efficient traversal. The image displayed on the screen highlights a sample graph. To store this graph in the database, it first needs to be converted into code, which then be stored in the GraphDB. The graph consists of two parts, clearly separated in the image by a horizontal line. The section below this line is referred to as Resource Description Framework (RDF) part, which resembles tuples in the relational database. The section above the line is referred to as RDF schema, which is similar to a database schema, primarily describing the graph's semantics. Typically, domain experts design the schema section. A well-designed schema enhances the precision of the graph semantics. The graph includes various types of elements or nodes, such as individuals, classes, and relationship. Individuals represent instances of real-world objects. For example, discrete mathematics and Joe are individuals in this graph. Entities are represented by classes, which correspond to specific instances. In this graph, course, associate professor, academic staff members are examples of classes. Is taught by and invokes are examples of relationships that primarily connects two entities. Generally, there are two types of relationship: object relationship and a data relationship. Object relationship connect two different objects, while data relationship link an object to a literal. Literals are general forms that can be specifically represented as numbers, strings, integer, dates, or times, with many data types borrowed from XML's basic data type. Now let us start converting the graph shown in the figure into corresponding code. Let us take the first statement. Discrete mathematics is taught by Joe Smith. This is called a triples. So we are going to write three different words
and we make sure we have a colon in front of all three words. Let us take another statement from the graph, which is nothing but Joe Smith is of type associate professor. So write this statement in the form of a triple. That is, Joe Smith is type of associate professor. Make sure you are having colon in front of every resources. Let us take one more example. Discrete mathematics is of type course. Any statement we take from the graph, that will be written in the form of a triples with the prefix as a colon. Now let us take a property is taught by. Now first of all we have to define is taught by is of type property. So we have to define is taught by is of type property. As I already told you, there are two different properties are there, object property and data type property. From this particular screen we are able to understand is taught by is an object property. Similarly, whenever you talk about an object property, the object property will have some resources on the left side and some resources on the right side. So is taught by is having a domain on one side, having a course. Similarly, is taught by is having another side that's called a range side as an academic staff member. Is taught by RDFS range academic staff member. And with respect to this particular graph, we can also see is taught by is defined as a subproperty of involves. So can be converted into corresponding statement as is taught by subproperty of involves. Now in this particular code, you can see there are few keywords having prefixes like RDFS and RDF and OWL. There is a reason why we have chosen RDF, RDFS and OWL. Before that, let us take one more statement in the graph, that is academic staff member, which is nothing but associate professor is a subclass of academic staff member. So there are few places we are using the keywords like RDFS. There are few places we are using OWL. Those are syntaxes of generating this graph. Those are syntactic sugar of this semantic web concepts. So wherever there is a type, we include the prefix as RDF. These are keywords. The terms which are underlined are keywords. Similarly, if you see, the very nature of this graph comes with so many user-defined terminologies. So for example, discrete mathematics, Joe. So these terminologies are non-keywords. So these non-keywords should be prefixed with some user-defined prefixes. Say for example, consider we are defining IO string. So we define what is the purpose of having an IO string? So IO string will define the namespace called std. So whenever we use cout or a cin statement, how do we use it in C++? std scope resolution cout and std scope resolution cin. So the namespace name, scope resolution and the class name. Similarly, with respect to semantic web, we use the namespace name colon the resource name, abc colon course, ABC colon assistant professor, ABC colon associate professor. So in total, if you see, this particular sample code is having the following prefixes: ABC, RDF, RDFS, and OWL. Few prefixes are comes as part of language construct, and few prefixes are user defined prefixes. Say for example ABC. So now let us include these prefixes as part of our previous code. Any prefixes to be included as part of the code, we have to use a statement like at prefix space the prefix name colon followed by some URI. Similarly, we use prefix for RDF and RDFS and OWL. So if it is in default keywords like RDF, RDFS and OWL, the prefixes will be given by the language construct itself. So the URIs we write here all are default or specified by the language construct. We cannot change that. But if you take the user defined prefixes like ABC, we can give our own URIs. It is not necessary that URIs should exist in the internet. All it expects is the URIs supposed to be in the proper format. That's all. So now you can see that a code snippet of a graph. The graph shown in the image is converted into corresponding code. Writing such complex code manually is difficult and is time consuming. Instead of writing such complex code, we can alternatively use the visual tools like Protégé to construct the similar graphs at ease. The tools facilitate creating such complex graphs using simple drag and drop and GUI based creation of graphs. Further, the tools facilitate converting the constructed graph into a code just in a click. As part of this tutorial, let us discuss creating the sample example graph using Protégé tool. Let us start creating schema part first. The schema consists of classes like courses, professor, associate professor, academic staff member, and a staff member. The schema also contains object relationships like involves and is taught by.
Let us start creating schema of this ontology first. The schema consists of classes, course, professor, associate professor, and assistant professor. Let us create these classes using Protégé tool. Here, the professor, associate professor, and assistant professor are subclass of the class called academic staff member. Let us create a class academic staff member first. Then, let us make sure assistant professor, associate professor, and professor are the classes subclass of academic staff member. For creating this subclass relationship, all we need to do is just drag and drop these classes into academic staff member. So you can see, moment you drag and drop the professor, assistant professor, and associate professor to an academic staff member, the subclass relationship will be automatically established. In the same line, the image shows the academic staff member is subclass of staff member. So let us create the staff member and drag and drop academic staff member into staff member. So automatically the academic staff member becomes subclass of staff member. The graph consists of set of object properties is stored by and involves. Let us create these object properties using object properties tab. Let me create is stored by as an object property and then involves as an object property. Similar to a class and subclass creation, just drag and drop is stored by into involves. It automatically establishes the subproperty relationship. The object property of the graph having two sides, domain and range side. Let us create this domain and range for involves. So click on the domain and navigate to the corresponding class and select. For instance, course is the class on the domain side. Similarly, click on the range side and select academic staff member as a range. Similarly, let us create domain and a range of is.by. So for is.by, the domain will be course and the range will be academic staff member. Of course, this domain and range will be automatically inherited from involves property. The graph consists of two data property, ID and a phone number. Let us create these data properties in Protégé using Data Properties tab. Let us create the ID and phone number using Data Properties tab. The ID and phone number are created as a child class of top data property. So the ID will have domain as well as range. The domain of ID is staff member, which is selected from the following tab. Similarly, the ID having a range as a literal. Now you can see the literal tab not only having the type as literal, you can select any one of the literal type, which includes date, time, everything is displayed in the screen. So as part of this, we have successfully created the schema part of this graph.
Let us start creating the individual section of the graph. Let us go to individuals by class tab and select the class for which you want to create an instance. Say for example, I want to create an instance of class course. So click on the diamond symbol and specify discrete mathematics. Now the instance has been created. Similarly, I want to create an instance as Joe Smith of type associate professor. Click on associate professor and then diamond symbol, then specify Joe. So I have created instance of associate professor. Let us connect the discrete mathematics to Joe Smith by using the property called is.by. Now navigate to course member and discrete mathematics and click on object property assertion. Specify the name of the object property, which is nothing but is.by, and specify the range, which is nothing but Joe. So we have created an object property is.by which connects DM with Joe. Now the entire graph has been successfully created using the tool Protégé. Let us save this graph into any one of the syntactic style. Now we can store the graph as an XML or Turtle or any different format. Though the formats are different, the graph it looks similar. Let us store the graph in the form of Turtle. Specify the graph name I mentioned as a course here. So extension of this graph is .owl, that is Web Ontology language. Let us open this file using Visual Studio Code. Now what you see here is set of triples. The entire file is set of triples. Say for example, involves object property, okay, domain, which is having a course. Now whatever the triples which we have created manually, here the same set of triples has been created using the tool called Protégé.
The tool successfully converts the graph as shown in the image to corresponding code.
After successfully converting the graph into corresponding code, that is course.owl file, let us load that owl file into a GraphDB. What you see here is an interface of GraphDB database. Now, if you want to load an owl file which you created, then you have to create a new repository. Specify name of an repository and create a repository. Moment you create a repository, now you can see there is a small symbol called connect repository. Click on the connect repository so that the repository become active. Now, whatever the owl file which you created, you can import the owl file using upload RDF file. Once you successfully import the owl file into this GraphDB environment, now you can operate with the code from the GraphDB. Now, if you want to see what exactly the graph which is loaded from the course.owl file, you can click on graph overview and you can see what are all the triples has been loaded from the course.owl to the graph environment. Let us click on the academic staff member and visual graph. Now you can visually interact with this graph. Now the color code represents different resources in the graph. So for example here, the DM and Joe are individuals in the graph. Just click on the arrow mark, you'll get the corresponding type information, property information, class information. Okay, all this information, whatever you created as part of the course.owl, you can visually interact. This is one advantage of this tool. Once you created and loaded a graph into this environment, you can write a simple SPARQL queries, which is much similar to SQL queries, to get information from this graph. Now, what you see in the screen is an example SPARQL query, which is equivalent to select star from a table name. The select star from table name retrieves all the tuples from the table. Similarly, this particular query consists of a pattern. The pattern is of the form question mark S, question mark P and question mark O. What are these question mark S, P, O stands for? All are variables. So S, P, O are selected randomly and can be used your own variables as well. So what happens here? The graph try to match the corresponding patterns from the existing code. So if you look at this, the discrete mathematics is taught by Joe, where the discrete mathematics can be an example of question mark S is taught by, can be considered as question mark P, and Joe Smith can be question mark O. These triple patterns will be matched against all the throughout the graph. So you can see there are so many triples can be matched from the existing graph. All these triples matched against this particular pattern will be the result. But we prefer only the random 10 results from the SPARQL query. So these 10 results will be displayed in the screen.
Now, let us replace the property question mark P by RDF type. Now, we have changed the pattern into question mark S, that is variable, RDF type and question mark O. So subject and object can be anything, but we are very particular about the property RDF type. So the result carries only two columns, that is question mark S and question mark O. These two resources, that is subject and object, connected by a property RDF type, will be returned as a result. We can further extend this particular pattern, like the same query is extended as the question mark O is RDF type will be owl class. So it means that it's like an uncondition. I want to have a statements with question mark S and the question mark O connected by RDF type, as well as the question mark O type must be an owl class. The corresponding pattern will be matched against the graph. The results will be written according to the patterns matched. Now, let us discuss how do we restrict our pattern for a specific subject. I have taken a complete URI of a subject course and mentioned as a subject followed by two variables. It means that I need to find a pattern with a subject as course and object and predicate can be anything. So whenever this particular pattern has been matched in the graph, the corresponding set of tuples will be returned. Now, just to change, I want to keep the course in the object part rather than the subject part. So whenever you change that, okay, any subject followed by any predicate and followed by the object as in course will be returned as a result. The OWL file loaded as part of GraphDB can also be accessed from any of the higher level programming language. So for example, we can access this GraphDB from Python, from Java, from Node.js, any programming languages. So the server programs written on any of these languages can interact with the GraphDB and they can retrieve whatever the results it needs. So, for example, as part of this particular presentation, we have some two demo programs written in Python where we have three variables. The Python program consists of three variables. These three variables are loaded with the parameters retrieved from the GraphDB. The parameters include query, endpoint address, header, or copied from the GraphDB's interface. So for example, the query can be any query which we discussed earlier. In addition to that, the endpoint address which can be obtained from GraphDB as well as the accepted header type. So all this information will be passed as a request from the application program to retrieve necessary information from the GraphDB. The GraphDB returns the result in the form of a JSON object. So the JSON object will be further passed to get the necessary results from the GraphDB from the application program point of view. From the literature point of view, there are few terminologies has been used interchangeably, such as semantic web, knowledge graph. So whenever we have a data in the form of a semantic web or a knowledge graph, how do we store the data? For storing the data, we use GraphDB. What are the applications of these areas? We can assume applications of either knowledge graph or semantic web or GraphDB. If there is a complex and interconnected data, then the best way to represent is knowledge graph based fields highlighted in this particular screen. So we have used knowledge graph for representing food related domain, building information model, IoT, and computer security, recommendation system, natural language processing, building ontology. So these domains are not limited with few applications. Thank you.